Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCA-DET, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the summary of the draft of the book. Artificial Hypothalamus and Mathematical Programming 4.0 for Industry 4.0 Cyber-Physical Systems. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. The course book has 5 parts. Part 1, Mathematical Programming and Cyber-Physical Systems. Part 2, Large-Scale Optimization Methodologies. Part 3, Integration of Mathematical Programming and Artificial Intelligence, and Part 4, Real-Life Applications. The course presents a holistic vision of applied mathematical programming, starting with the theoretical foundations of classical optimization, and ending with the implementation of highly complex software solutions. According to the state of the art, the following are studied: artificial brains, parallel and distributed analytics, mathematical modeling, parallel computing, the basic algorithms, and large-scale optimization theories. Given the current technological evolution, the course integrates, at the theoretical level, artificial intelligence and mathematical programming, and on a practical level, the design, implementation of optimization solutions, applied to real problems of companies. Part I: Mathematical Programming and Cyber-Physical Systems. Presentation of the mathematical foundations for the solution of optimization problems. It includes the economic interpretation of optimization models and MPEC, mathematical programming with equilibrium constraints, problems. The different formats of optimization problems and the algorithms to solve them are also briefly presented. Theme plan: Artificial brains. The future, Mathematical Programming 4.0. Parallel and distributed analysis. Optimization basics. Economics, fundamentals, and optimization technologies. Chapter 1-1, The Future, Mathematical Programming 4.0. This chapter is aimed to introduce the concepts of the vision of the author about the role of the mathematical programming as part of the Industrial Revolution 4.0. The book develops the mathematical and technological foundations that support this view. The mathematical programming, MP, and in general the mathematical modeling based on algebraic equations, requires new ideas to meet the challenges of the future, which already is bringing fundamental changes in the way of doing things. This is reflected in the new Industrial Revolution, called Industry 4.0. Chapter 1-2a, Fundamentals of Optimization. A summary of the basics that are required to work on optimization and meet the strong relationships between economics and mathematical programming. Mathematical topics: Lagrange theory, duality theory, and Karush-Kuhn-Tucker, KKT, conditions. Chapter 1-2, Economics Fundamentals, economic topics: Lagrange multipliers, dual variables, marginal costs, markets modeling, and equilibrium modeling. Special interest is given to mathematical problems with equilibrium constraints, MPEC. Part 2: Large-Scale Optimization Methodologies. The detailed topic plan is divided into 12 topics. Enterprise-wide optimization systems. Technical economic interpretation of large-scale methodologies. J.F. Bender's theory, variations, and improvements. Stochastic programming and risk management, fundamentals. J.F. Bender's dynamic and stochastic theory. Lagrangian relaxation and Dantzig-Wolff decomposition. Cross-decomposition. Stochastic and dynamic theory. Other methodologies. Asynchronous parallel optimization. Expert optimization systems. Autonomous, real-time distributed optimization, and real-world applications. Chapter 2-1a, Mathematical Organization of the Artificial Hypothalamus, Partitioning and Decomposition of Large-Scale Models. Most of the things and processes that humans use have been totally affected by technology, which has opened up to the human imagination producing previously unsuspected results. Mathematical modeling should not escape this process. From the discovery of the mathematical foundations that serve to establish the laws that govern physical, industrial, economic, and social processes, and with them build increasingly powerful mathematical models and calculation algorithms, today all the knowledge and technology is available to develop a new artificial intelligence that emulates the human brain in any type of human organization. It can be called the mathematical hypothalamus of the organization. Chapter 2.1b, Organization. Mathematical hypothalamus. Parallel optimization as an artificial neural network. Making a parallel with neural nets, the concept of problem family can be assimilated to a neuron class, and the optimization process can be defined as a complex communication system between smart neurons. Basic neurons, perceptron, are based on perceptions that are added and processed to explain the behavior of the system based on adjustment of observations to history, but without ability to internally process the signals receiving. Chapter 2-2, J. F. Bender's Theory, Variations and Enhancements. In 1962, J. F. Benders published his seminal theory in the paper Partitioning Procedures for Solving Mixed Variables Programming Problems Oriented to Optimization of Mixed Integer Problems, MIP, that was been the origin of multiples methodologies oriented to solve large-scale problems related with stochastic complex combinatorial and/or dynamic systems. Since its formulation in 1962, the researchers in Bender's theory, BT, have proven that BT is an effective methodology to solve complex problems that cannot be solved using only best basic optimization algorithms, Plex, Gurobi, Express. 2. Algorithms based in Bender's theory can solve NP-hard, non-deterministic polynomial time problems in reasonable time. For this type of problems, BT has proven to be an effective methodology to solve complex problems that cannot be solved using best mathematical solvers. BT is a mature methodology that is in the accelerated growing phase, and there is a gap between the research in mathematical programming and the application of the large-scale methodologies in real-world solutions. Chapter 2-3, Stochastic Programming and Risk Management, Fundamentals. In the field of mathematical optimization, stochastic programming, SP, and robust optimization, RO, are frameworks for modeling optimization problems that involve uncertainty. This chapter considers four aspects about stochastic optimization. They are: stochastic programming, SP, based on scenarios, also known as non-anticipative stochastic programming. SP considers multiple scenarios, associating each of them with a probability of occurrence, and the model determines the best decision before the occurrence of the scenario, non-anticipative decisions. The risk management associated with decisions is a fundamental part of the analysis, considering that optimize just the expected value of the objective function may lead to decision highly risk-prone, with greater risk, volatility. Basic concepts about the use of large-scale methodologies to solve complex SP problems due to the amount of scenarios involved in the analysis. 4. Robust optimization, RO, is a field of optimization theory that deals with optimization problems in which a certain measure of robustness is sought in the face of uncertainty that can be represented as deterministic variability in the value of the parameters of the problem itself and/or its solution. Chapter 2-4, Dynamic and Stochastic Bender's Theory. This chapter presents a review of the use of the theories of partition and decomposition of Bender's, BT, and its variations, emphasizing its use in complex dynamic stochastic systems. It includes theoretical considerations about the solution of dynamic optimization problems integrating the Bender's theory, the dynamic programming approach, and the concepts of discrete control theory. Two methodologies are presented to solve the problem: nested Bender's decomposition, NB, and generalized dual dynamic programming, GDDP, including their extensions to stochastic programming, SP. Chapter 2-5, GDDP GSDDP, Implementation and Electric Sector Applications. This chapter is oriented to study the computational implementation of the generalized dual dynamic programming, GDDP, and generalized stochastic dual dynamic programming, GSDDP. Implementation focuses on dynamic and/or stochastic models, The concepts presented are typical of the GDDP/GSDDP. The implementation only presents considerations for sequential computing, but they are critical to the implementation of parallel GDDP/GSDDP algorithms, which is presented in a later chapter. The described process has been implemented in Optex Expert Optimization System, Velasquez 2018. Chapter 2-6, Lagrangian and Dantzig-Wolff Relaxation and Decomposition Case, Oil Production Optimization. This chapter introduces two large-scale optimization methodologies, Lagrangian relaxation and the Dantzig-Wolff decomposition principle, which are strongly related to the basic concept, relaxation of restrictions of the original problem to break it into two problems, one master and another slave. The slave generates information to send problem can be decomposing to facilitate the solution of the entire problem. The slave problem generates information to be sent to the master problem, and it may be decomposed in several sub-problems to facilitate the resolution of the entire problem. Chapter 2-7, Stochastic and Dynamic Cross-Decomposition Case, Expansion of Multisectoral Industrial Systems. Cross-decomposition, CD, is an approach to solve large-scale stochastic dynamic optimization problems using the combination of large-scale optimization methodologies developed by Benjamin Van Roy. CD presents the principles for integrating Bender's partition and decomposition theory, BT, with Lagrangian relaxation and/or with Dantzig-Wolff decomposition, DWD. CD is applied when the coordinator subproblem partition has been performed and the math modeler wants to perform a new partition or decomposition on the coordinator, and/or in the subproblem, using a different, or the same basic theory, than the one previously used. Chapter 2-8a, Generalized Disjunctive Programming. Chapter 2-8b, B-level optimization. Chapter 2-8c, Surrogate Programming. Primal dual surrogate algorithm case, economic load dispatch including transmission losses. This chapter presents the surrogate mathematical programming, SMP, developed by Greenberg and Pierce-Callas, in 1970, and the design and implementation of the PDS, primal dual surrogate algorithm for nonlinear convex programming developed by Velasquez, in 1986. Chapter 2-8d, Mathematical Programming with Equilibrium Constraints, MPEC. Chapter 2-9, Asynchronous Parallel Optimization. In the prologue of the book Parallel Optimization, Theory, Algorithms and Applications, wrote by Sensor and Xenios, in 1997, the Professor Dantzig said, "The fascinating new world of parallel optimization using parallel processors, computers capable of doing an enormous number of complex operations in a nanosecond." Additionally, he said, according to an old adage, "The whole can sometimes be much more than the sum of its parts." I am thoroughly in agreement with the authors' belief in the added value of bringing together applications, mathematical algorithms and parallel computing techniques. This is exactly what the mathematical modeler found true in parallel optimization. Chapter 2-10, Real-time Distributed Optimization in Cyber-Physical Systems. Real-time distributed optimization is the distribution of the optimization process in many agents that act simultaneous and independently when they received information from its exogenous environment. The process can be summarized in the following steps. From a top-down analysis, mathematical is possible to construct mathematical or logical rules of interaction between multiple agents, representing each part of the system, which can represent the state of the reality. 2. Starting from the math/logic rules, following an approach bottom-up, is possible to build segmented/atomized models of the real world. Using asynchronous optimization processing, it is possible to define the actions of an agent that keep the system on the optimality path in a cyber-physical system. The founder of HI has focused his scientific research on the development and incorporation of parallel optimization algorithms to Optex. The algorithms created are: Primal Dual Subrogate Algorithm, PDS. Multi-Level Bender's Partition, MBP. Generalized Stochastic Dual Dynamic Programming, GSDDP. Multi-Bender's Decomposition, MBD, and Sliding Optimization. These algorithms, and others more existing in the literature, support the implementation of artificial brains. Part 3: Integration of Mathematical Programming and Artificial Intelligence. Presentation of a new vision of mathematical programming. I. Structured mathematical modeling, standardization of the formulation of mathematical models to make algebraic formulation independent of optimization technologies. This makes it easy to port mathematical models between multiple optimization technologies. 2. Robotization, making use of artificial intelligence concepts to capitalize on the lessons learned in expert systems to facilitate the construction of the mega models of the future. Theme plan. Relational databases and mathematical programming. Structured mathematical modeling. Tutorial, an example of structured mathematical modeling. Expert optimization systems. Cognitive robots, intelligent algorithms that build advanced analytical algorithms. OptX expert optimization system, a cognitive robot for mathematical programming, and advanced predictive analytics using mathematical programming. Part 4, optimization of industrial systems. This part contains cases based on experiences in real engineering projects. Each chapter includes the algebraic formulation and the design of the computational implementation of the models. Several chapters include programs in multiple optimization technologies, GAMS, C, AMPL, IBM OPL, Mosel, Python Pyomo, and others. Theme plan. Enterprise-wide optimization. Traditional and state-of-the-art models. Industrial supply chain modeling. Implementation of a sales and operations planning model. Tutorial, SandOp for a brewery chain. Integrated planning of financial and industrial operations. Advanced optimization in bio-industrial supply chains. Design of resilient logistics networks. Case, distribution in the beverage industry. Industrial systems programming using continuous time modeling. Multi-level dynamic inventory using stochastic optimization. Mixing in industrial processes. Case, production, distribution and marketing of oil. Modeling of chemical processes. Case, advanced optimization in cement plants. Real-time optimization of pipelines using non-convex Hulls approximations. Industrial asset maintenance optimization. Integrated regional planning. Vehicle routing problem. Tutorial on variations. Transportation revenue management using machine learning and optimization. Optimization of continuous schedules. Case, port logistics operations. Optimization of discrete schedules. Case, programming of universities and colleges. Human resources analytics. Energy market modeling. Distributed smart grid optimization, in real time. Advanced predictive analytics I, simultaneous equation demand and market share modeling, and Advanced predictive analytics 2, revenue management fundamentals. Part 5, software implementation. Applied teaching of the programming of highly complex mathematical models. To do this, an ALMS, algebraic language modeling system, optimization technology is used, like GAMS, AMPL, or other, and OptX optimization expert system supported by RCA-DEET. Theme plan. Fundamentals of optimization technologies. Mathematical models and data models. Structured mathematical modeling, case, electricity and gas model. OptX Modeler I, algebraic database language. OptX Word Excel. OptX Modeler 2, advanced services. Feasibility analysis. Deterministic models. Parametric optimization. Stochastic optimization. Large-scale optimization technologies. Asynchronous parallel optimization. Artificial hippocampus, cutting planes and convex hulls. Artificial hypothalamus, and advanced optimization. Math heuristics. Disjunctive programming, and bi-level optimization. Alfred North Whitehead affirmed, algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world. The importance of this phrase lies in the fact that all modern mathematics is based on algebraic models that become algorithms, that use all the power of current computer technologies. Thank you for your attention.